So this will be a discussion of problem number 4 from the 2021 AP Calculus AB and BC exam. This type of question is pretty typical to show up in a free response set. This one presents us with this graph of f. They tell us that it's defined on the interval from -4 to 6, and it's 4 line segments. And then they define this function g, and g is dependent on f, but you notice g is defined as a definite integral, and the input variable to g is that upper limit of integration, the x. So question A here is a question about g, and they ask us on what open intervals is the graph of g concave up. So hopefully you read that and you think, well, concavity, I'm going to have to take a second derivative. So before you get there, you've obviously got to take a first derivative. And if you try to take the derivative of this function g right here, what you're going to have to utilize is the fundamental theorem of calculus. So that allows us to take the derivative of this type of function by simply taking the function from the integral, so taking the integrand and replacing the holding variable, the t in this case, with the upper limit of integration x. So g prime of x is equal to f of x, so this is really a graph of g prime. And then if I take a second derivative, I'm going to end up with g double prime coinciding with f prime. So hopefully we recognize that on this graph of g prime, to determine values of the second derivative, we're going to have to look at slope. And the slope is positive on this stretch. The slope is positive on this stretch. Those are the two intervals. So the x values from -4 to -2 and from 2 to 6, where g is concave up. We're not including anything between because we've got negative slope, so negative value for g double prime, negative slope, negative value for g double prime again here. What has to be within your line to get credit for the reasoning? This is the most significant thing, right? Showing that you know that the second derivative has to be positive in order for you to be concave up somewhere, and these are the intervals where it happens. In part B, they give us a new function, p of x, and p of x is defined as g of x times f of x. We're asked to find p prime of 3. So if you look at p of x and you think about how you're going to take the derivative, hopefully right away you recognize that it's going to require a product rule. So that's what you see across my top line right here. And then we have to evaluate it at 3. So I tried to kind of color code this because there's some values that are a little bit more difficult to determine than others here. But I'm going to have to evaluate g prime at 3, f at 3, then add on g evaluated at 3 times f prime of 3. Now f of 3 and f prime of 3 are pretty straightforward to determine. You're going to get those straight from the graph. This is a graph of f after all. So f of 3 is simply going to be the y value on this graph at 3, and the y value on this graph at 3 is -3. So I've replaced f of 3 with -3, and then f prime of 3. Well, on a graph of f, we're going to have to look at the slope at 3 to determine f prime of 3. And the slope of this stretch of the graph, if I do a simple rise over run, is just going to be 1 over 1. So slope of the graph is 1 at 3, therefore f prime of 3 is 1. Now, g prime of 3. Back in part A, we determined that g prime is equal to f. So g prime of 3 is really equal to f of 3, and f of 3 is -3. We just made that replacement when we went from here to here, so we're going to make it again as we go from this new instance of f of 3 to this next line. The most difficult calculation here is for g of 3. So for g of 3, what you're going to have to do is you're going to have to put 3 in place of the x in g and try to evaluate. Now, if you're trying to evaluate this integral right here, you're going to have to use area arguments, and you have to be cautious because a portion of this stretch of the graph of f is above the x-axis and a portion's below. So what I have is I have this triangle that sits above the x-axis from 0 to 1, and I have a congruent triangle that sits below the x-axis from 1 to 2. So that would be the area of each of those triangles would be 1/2 base of 1, height of 4. I've got the positive calculation here, but then I'm subtracting off that same area because, like a definite integral is defined to do, it computes a signed area, not just an area. So space above is going to come back as positive, space below is going to come back as negative. So these effectively cancel with each other. And then the last little portion of this graph on the interval from 1 excuse me, from 2, I'm sorry, I already considered from 1 to 2. That was this triangle below the x-axis, but the last little portion of this region spans the x-axis from 2 to 3. What I have sitting here is I have a trapezoid. So my parallel sides would have a height of 4 and a height of 3. So I'm taking the average of the parallel sides and then times the distance between them, which is 1 unit. Now I am subtracting that off because that space is also below the x-axis. Now I don't have to do any simplifying. I don't even have to cancel these that I canceled a few seconds ago. This line right here would receive full credit on the AP exam, but if you wanted to try to clean it up, you should end up with an answer of 11/2. Part C is a limit that we're asked to determine. And the limit is going to involve g of x within the numerator and a different expression within the denominator. Now we're checking the limit as we approach 2, so I'm just going to put 2 in place of all my x's and see what happens. Now I am being kind of cautious here. I haven't used an equal sign at all across this line, and the reason for that is because I don't want to claim that something is equal to something that's undefined or something is equal to something that's indeterminate. And so what I notice about this denominator is I do get 0 within it, so I am going to have to be careful with my notation, avoid using the equal signs. If I work out the numerator like we did back in part B, I'm going to have to put 2 in place of this x and use area arguments to determine the value of g of 2. We kind of did that back in part B. We just aren't considering the stretch of the x-axis from 2 to 3 anymore. From 0 to 2, it's just those two triangles we were talking about a couple minutes ago. One above, one below, they're congruent to each other, so the value of this integral is actually going to be 0. 0/0 is an indeterminate form. It does signal that we can apply L'Hopital's rule, right? 0/0 is something that gives us the green light to go ahead and use L'Hopital's rule. And so when we apply L'Hopital's rule, we take the rate of change of the numerator, divide it by the rate of change of the denominator, and we reevaluate the limit as we approach the same value. So g prime of 2 is what I end up with in the numerator. 2 times 2 minus 2 is what I get in the denominator. You will notice I've used equal signs across this line, and what told me I was going to be able to do that here is this denominator. This denominator is not 0 anymore, so I am going to get an answer that's going to be okay when this comes to a close. This right here is not an acceptable way to leave your answer because it depends on g prime. Well, what's g prime equal to? Well, earlier in the problem, we established the fact that g prime was equal to f. So f of 2 and g prime of 2 are the same value. This also would not be an acceptable way to leave your answer because it depends on f. So what is f of 2? Well, f of 2 is just going to be the y value from this graph at 2, which is -4. This would be an acceptable way to leave your answer. It's easy enough to recognize how that simplifies. This would be the simplified version of that answer. And then the last part of this is one that asks us to do several things. So we are asked to find the average rate of change of g on the interval -4 to 2. So average rate of change is simply going to be a slope calculation applied to the function using the endpoints of the interval that you're asked to do it across. So g of -4 minus g of 2 over -4 minus 2. G of -4, well, that's something that's going to be a little bit tricky to determine. I'm going to do what we've done a few times already. I'm going to have to put -4 in place of that x. Now when I do that for the first time throughout our work in this problem, these limits of integration are not in increasing order when we go from lower to upper. To use signed area arguments the way that we've defined them to work, we're going to have to flip those limits of integration so that the smaller numerical value is at the bottom. I have no idea what I wrote on this next line. This next line is totally not okay. Let me pause the video and try to make a quick adjustment here. Okay, this looks a little better. I don't know exactly how I did that. I do have the right calculation here, but I don't know how I accidentally had the wrong limits of integration there. So when I negate the integral, I simply swap the limits of integration. And if I'm looking for the signed area between this graph and the x-axis on the interval -4 to 0, I see a triangle that spans the x-axis from -4 to 2. So the area of that triangle would be 1/2, a base of 2 units, and then a height of 6 units. And I'm going to have to add on to that the area of this trapezoid that you see here in red that spans the x-axis from -2 to 0. The parallel sides on that trapezoid have a height of 6 and a height of 4. So I'm adding the length of the parallel sides together and dividing by 2, so average of the parallel sides, and then times the distance between them. My initial attempt at this, I actually goofed. I had the right thing shown here, and I just totally botched the middle school math to simplify it to -16. So I should end up with -16 for g of -4. Now I don't have to do that simplification. What I have highlighted here, as long as you include the negative, that would receive full credit. So if I just transfer that into this position, I'd be okay in the eyes of the College Board graders. But I did simplify it to -16, and we'll talk about why in a minute here. And then I also need to know g of 2. Well, we already found g of 2 in the previous part of the problem. G of 2 is the stretch of the x-axis where we see the triangle that sits above the x-axis and then the congruent triangle that sits below. So g of 2 is 0. So my average rate of change is going to be -16 minus 0, right? G of -4 minus g of 2 divided by -4 minus 2. That will simplify to 8/3. Look at the secondary part of this question. Does the mean value theorem guarantee a value c between -4 and 2 at which g prime of c is going to equal that average rate of change? Justify your answer. So the mean value theorem has two requirements in order to be able to use it. You have to be continuous and you have to be differentiable. Now what they tell us in the problem statement is that f is continuous. This is a graph of f, but it's also a graph of g prime. Since g prime is equal to f of x and f is continuous, g prime is differentiable, and if g prime is differentiable, it's also got to be continuous. So these two words being on your page in reference to g are the things that need to be there in order for you to receive that justification point. G is oh my gosh, I have another mess up here. I think I can fix this one on the fly. I didn't mean to say g prime is continuous and differentiable. G prime is actually not differentiable due to the cusps that we see on the graph in several spots here. But g of x, now that I've erased that prime, g of x is continuous and differentiable, so that looks a little bit better on the interval -4 to 2. Green light to use the mean value theorem, and the mean value theorem is going to guarantee that g prime of c is going to equal this average rate of change at least once on the interval -4 to 2. What's kind of nice about this particular situation, this is actually a graph of g prime, right? F and g prime are equal to each other. So can we find a place on the graph where g is equal to 8/3? 8/3 would be what, 2 2/3? Well, yeah, 2 2/3 would be, somewhere in this range on the graph. And yeah, clearly we do hit that on the interval. But that is number 4 from the 2021 AP Calc AB and BC exam.